In this video, we'll take a look at nucleophilic addition to aldehydes and ketones. So this reaction occurs when you have a nucleophile that adds to a carbonyl species. As the name suggests, the carbonyl species doesn't have to be an aldehyde or ketone, but this is the best place to start because they're the simplest types of reactions. The general reaction scheme is a nucleophile will add to the carbonyl, removing the pi bond between the carbon and oxygen and creating that as the fourth bond in a tetrahedral geometry. So this is the general scheme. The identity of the nucleophile can vary a lot. It doesn't necessarily have to have a negative charge as I've shown here, but it must have a lone pair. So we'll go through some specific nucleophiles that can do this type of reaction, but with that we'll go right into the mechanism. So this mechanism involves using that lone pair or the negative charge, depending on your nucleophile, to form a bond between the nucleophile and the carbonyl carbon, which is the electrophile. It's the electrophile in this case because we have a dipole moment between the carbon and the oxygen. The oxygen is very electronegative. It has partial negative charge because of this electronegativity, which makes the carbonyl carbon electron deficient with this partial positive charge. This is the driving force, this Coulombic interaction between the nucleophile and the carbonyl carbon that creates that bond. And then at the same time, we have this kind of pseudo leaving group where the pi bond of the carbonyl compound breaks onto the oxygen with the partial negative charge onto the very strongly electronegative atom. So if we didn't have this happen in this concerted step, we would then have 5 bonds at our carbonyl carbon, which is not allowed. Carbon must have 4 bonds. It cannot have an expanded octet. So once that occurs, the nucleophile will add to what was the carbonyl carbon, and it will add in this way that it has been drawn, and this will then create, depending on what your R groups are, you'll have this chiral compound now. Now, depending on the identities of R, it may or may not be chiral, because if R's are identical, then it won't be chiral and you don't have to worry about this. But let's say they're different, then there's no preference on if the nucleophile will approach from the bottom face or the top face, which means that this intermediate here is going to be racemic. You're going to have a 50-50 mixture of the both enantiomers. So in that case, you're still having an achiral mixture at the end, even though you have chiral species within that. And again, this is due to the fact that the carbonyl is planar to begin with, so there's no preference on which face the nucleophile can approach. Then usually this negative charge that's left on the oxygen, the carbonyl oxygen, is protonated with some kind of acid workup. It depends on the reaction conditions, but it can be a lot of different things. But all that's going to do is protonate that to an alcohol as shown here in a typical Lewis acid Lewis base reaction, and then you'll end up still with your achiral product, which is a 50-50 mixture of enantiomers, your racemic mixture, again, assuming the two R's here are not identical. All right, now there's a few observations and comments I want to make here about this type of mechanism. So first of all, pi bonds are relatively weak, which is why this can occur in the first place. Since typically this is confusing for students because you think of double bonds as stronger than single bonds. And that is true if you treat both bonds. Remember, a double bond has 2 bonds in it, a sigma character and a pi character, and the sum of that energy is greater than just a single bond. But the sigma character is adding more energy than the pi character of the double bond, which is why we say the pi bond alone is relatively weak. And that's why it can act as what I call this like pseudo leaving group. You can use that bond to fulfill the octet on that carbon by dumping those electrons onto the oxygen, and this is why this type of mechanism is allowed. Secondly, nucleophile adds to the carbonyl, again, based on what I was just saying with the pi bond, it's no like substitution reaction, there's no real leaving group, it's just the pi bond is breaking, and in replace of that pi bond is the new bond between the carbon and whatever your nucleophile is. Thirdly, the carbonyl carbon, its hybridization changes. It goes from sp2 in this planar geometry with 3 electron groups, and it goes to sp3 in this tetrahedral shape in both the intermediate and the product. Again, this can be very important. It depends on the context of the situation, but this kind of illustrates why this is an addition reaction and not a substitution, because you're changing the hybridization. That's among one of many things that's occurring here. And lastly, this sp3 carbon may become chiral. It depends on the identity of R groups, like we've already mentioned, but if they are different, then you are absolutely going to get a racemic mixture, because you cannot go from an achiral starting material to a chiral product. All right, another important thing to mention about this type of reaction is that aldehydes are more electrophilic than ketones. And the reason for this is that alkyl groups are electron donating through hyperconjugation. So this hyperconjugation phenomenon is the exact same one that stabilizes a carbocation. A more substituted carbocation is being stabilized by these alkyl groups, which can essentially donate their electrons to that positive charge through this phenomenon. It's called hyperconjugation, which again stabilizes that positive charge and in essence would make it less electrophilic. So this is the exact same phenomenon that's occurring in aldehydes and ketones, and why aldehydes are more electrophilic. So if we look at this aldehyde, we only have one alkyl group. Again, we still have the carbonyl species, so we have a dipole between the oxygen and the carbon. So this carbon does have a partial positive, but this methyl group here, the alkyl group, is electron donating through hyperconjugation. So what you can think of, you have this full dipole here, and then you can have some kind of like partial dipole that you can think about through hyperconjugation. And I will draw it as a dotted dipole like this, where you do have some electron density getting donated to that carbonyl carbon, which is making it less electronegative than, or less electrophilic, excuse me, than if there was no alkyl group there at all. So now if you compare that to a ketone that has two alkyl groups, you have this hyperconjugation occurring twice. So again, you have the dipole of the carbonyl oxygen to the carbonyl carbon, making this electrophilic to begin with, but then you have two alkyl groups that are electron donating through hyperconjugation, which again stabilizes that partial positive charge on the carbonyl carbon, which makes it less electrophilic. So in the end, this is exactly why aldehydes are in general more electrophilic than ketones, because they simply have less alkyl groups to stabilize that partial positive charge, making them more electrophilic. So that is the aldehyde phenomenon. And then lastly, let's talk about how we can promote these reactions. And acid catalyst is one way to do this. This can promote nucleophilic addition to carbonyls, and the reasoning is this mechanism here. So again, those oxygens are Lewis basic. So we think about these carbonyls compounds as having the electrophilic feature of the carbonyl, which is Lewis acidic, but that's not the only thing that's going on. We still have an oxygen that is Lewis basic that can easily be protonated by, again, some acid, whatever acid you have. Let's consider H3O plus, for example, just protonated water. You could grab that proton and you would get this protonated carbonyl. Now, the reason this makes the carbonyl carbon more electrophilic is you have this resonance structure now where there is actually a carbocation at this carbonyl carbon, which is now extremely electrophilic. So this increases the electrophilicity of the carbonyl carbon, which makes it more susceptible to nucleophilic addition from some nucleophile that you may have in your reaction mixture. So because of that, this is commonly used for ketones specifically because of the previous mention that they have this extended hyperconjugation, which makes the carbonyl carbon less electrophilic. So if you have acid catalyst, it will further promote the reaction and just drive your yields up. All right, for the remainder of the video, we'll take a look at several questions. So our question here is draw a complete mechanism that predicts the product. So we have a carbonyl species here, it's specifically a ketone. We know that because we have two R groups on either side of the carbonyl. Now we have to consider what our reagents are. Well, this is a Grignard. And we know that because of the magnesium bromide complex here. So Grignards, we generally treat them as a R minus, a carbanion, essentially. So what this can be treated as then is our Grignard here has a negative charge on the methyl carbon, and then this MgBr we treat as a positive charge. So essentially you treat this as it's an ionic species where you're delivering a carbanion to your system. Okay, so now that's very important to note because now we have a suitable electrophile. If we look at our ketone here, again, we have a dipole between the carbonyl carbon and the oxygen. So there is a partial negative charge on the oxygen and a partial positive charge on the carbonyl. And then we are delivering this methyl negative charge and separating from the magnesium bromide here. And this will attack the carbonyl carbon. And we're now creating a new carbon-carbon bond. And again, at the same time, we are cleaving the pi bond of the carbonyl, because if we weren't, there would be 5 bonds there. So that has to happen. And again, the pi bond isn't particularly strong, so this can happen and is relatively promoted. Now, this will give us this product, right, with a negative charge on the oxygen, but we do have this magnesium bromide floating around, so usually that negative charge is balanced by the magnesium bromide. I'll explicitly draw it here, right, something like this. Now, we're not finished here. Well, we have a couple things to consider. Is this a chiral species to begin with? Is the first thing to talk about. And we have 2 methyl groups at this position. So this is achiral, so we don't have to worry about it being racemic or anything like that. It's simply achiral because of the identical groups. It's the same as if they were 2 hydrogens at that position. Now, there's a second reagent here, though, and it's acid water. So we have H3O+, which I'm going to draw it like this, right? So now what's going to happen with our intermediate? Well, the negative charge on the oxygen is going to take that proton, and that is essentially going to separate from the magnesium bromide. So you're going to end up with this product, right? And then you have magnesium bromide floating around and water. All right, so once again, we are asked to draw a complete mechanism that predicts the product. So here we have an aldehyde now, because we have this, our carbonyl species is an aldehyde because we have the proton on the other side of the carbonyl. Now, recall that aldehydes are more electrophilic than ketones. And in this case, it's not going to matter very much, but we should always remember that because you won't know necessarily when it's going to matter and when it won't matter. So here we have an aldehyde, so now we have to look at our reagent. This is an organolithium. And you can treat these very similarly to Grignards in the sense that it's ionic, and there's a negative charge on this carbon, and the lithium is a positive charge. So this has some covalent and ionic character, but as far as mechanisms are concerned, you can simply show this as having a negative charge on that carbon, making it a carbanion, and that is going to be your nucleophile. And again, it's a carbon nucleophile, so that's particularly useful because you can make new carbon-carbon bonds. So here's our nucleophile. Then we go to our starting material is this aldehyde, benzaldehyde to be specific. It has this phenyl group as the R group of our aldehyde here. Now, we have to consider how this is going to bond. Well, the carbanion has the lone pair there that I haven't drawn, but that's what gives it the negative charge. This will attack the carbonyl carbon, which again is partial positive charge because of the dipole to the oxygen. Then we're going to cleave the pi bond onto the oxygen, again, carbonyl oxygen, and create this species. And now this is where our nucleophile goes, which is 4 carbons. So we have to count 1, 2, 3, 4. So this is 1, 2, 3, 4. Okay, so that can be a challenge for students as well because you have to, how do you know how many carbons there are? Well, you simply count them and keep track of them in your mechanism. So we know that we're creating this bond between carbon 1 and the carbonyl. Here's carbon 1 and the carbonyl, and then everything else is unchanged, a part of carbon 1, bound to carbon 1. And this oxygen now has a negative charge because we've cleaved that pi bond onto it, and then the lithium will balance out that charges, similarly to the magnesium bromide in the Grignard reaction. Okay, and then lastly, we have acid workup again. This simply gets rid of the lithium. And we have acid workup with H3O+. So again, drawn like this to illustrate that you're removing this proton, and this reproduces water. And again, if the question is what happens to the lithium, there's a lot of things that it can do. So typically it's acceptable to just draw it as 1, 2, 3, 4 as just lithium plus as a byproduct, and then water. It depends on what else is in your reaction species. It could be like lithium chloride. If you had HCl as your acid workup, there's a lot of things like that. But there's one thing we didn't consider here, and it's what about the chirality or possible chirality of the intermediate and product. So at this point where we create this now tetrahedral intermediate, this is a chiral position because all the groups are different. There's 4 groups, so we're going to make a racemic mixture of the intermediates and then a racemic mixture of the products. Right, so there's no preference over either enantiomer in this case, and usually in these types of reactions there won't be a preference, but there is some stereochemical control, and we'll get into some of those options in future videos. All right, this is the last question for this video, and again we're asked to draw a complete mechanism that predicts the product. So here we have an alkyne with a terminal proton. So terminal protons in alkynes we know are acidic because of the hybridization of the carbon that it's bound to. The sp hybridization makes that proton very acidic, so something like sodium amide is a strong enough base that can remove it, which is what we have here. Sodium amide, extremely strong base. This will undergo an acid-base reaction at that proton and form then a carbanion. Giving us this. Now, the carbanion, again, is a good carbon nucleophile. This could attack an electrophile if we had one. So if we look at the next reaction arrow, that's exactly what we have. We have an aldehyde that is an excellent electrophile. So that is exactly what occurs here. The carbanion will attack the carbonyl, again, because the carbonyl has this dipole moment, which increases the electrophilicity there and allows for this attack to occur. And then simultaneously, we cleave the pi bond, which again is relatively weak. And now this is going to make a chiral species. Now, a lot of students get confused at this point of how do we now draw this product? Well, again, this proton doesn't necessarily need to be drawn. We're going to make a sp3 chiral center there so that that position will be assumed to have that proton, whether it's drawn or not. So what I like to think about then is you essentially replace the group you're adding where the hydrogen is, and you don't draw that hydrogen in because it's going to be implied in the product. So that's how I think about it. But now the thing that you should always do is number your carbons to make sure that you keep track throughout. So we're creating a bond between carbon 1 and the carbonyl, right? So I'm simply going to start by drawing our carbonyl with only one bond because we're breaking the pi bond here. So it'll have a negative charge there and a positive counterion of the sodium. And then the T-butyl group remains unchanged. That's to the right of the carbonyl. And then we're now going to create a bond to the carbonyl, which is now the alkyne proton, the alkyne carbon rather, which is carbon 1, right? And carbon 1 is triply bound to carbon 2. And then we have carbons 3 and 4 that finish out this molecule, right? So now the question is this chiral? And again, that hydrogen I didn't draw here in this case because now it's assumed to be there to fulfill the octet of that carbon. So it is chiral then, since the hydrogen would make the fourth bond. So again, this must be racemic mixture because you can't go from an achiral starting material to a chiral products. So you get this racemic intermediate. And then we have H3O plus to as an acid workup here to remove the sodium and give us an alcohol. So this can attack like this. All right, I'm abbreviating this now. Look at the previous examples that hydrogen is bound to the oxygen. This is going to cleave onto the oxygen, so I'm abbreviating it somewhat, but hopefully this illustrates that you're going to get water as a byproduct and then the alcohol. So now you get this final product. Right, again, where this is carbon 1, 2, 3, and 4. Right, T-butyl group, the alcohol, and the proton is there, and again, this is racemic. All right, so that is all I had for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a suggestion or a topic idea, anything like that, please feel free to leave it down in the comment section below, and I'll get to it as soon as possible. So with that, I hope you all have a great day, and I'll see you in the next video.